All right, ladies and gentlemen, welcome back. Today we're going to discuss an extension of the problem of the model that we considered in the previous lecture. That would be multiple linear regression. And after that, actually, we're going to take a look at nonlinear regression. Right? So how do you make a more sophisticated models based on something that you may see in your residuals plot? But first, let's kind of discuss what a multiple regression is and what it looks like. In the previous lecture, when we talked about the simple linear regression, we said the reason why it's called simple is because there is only one predictor variable x. So independent variable, we're limiting that number of independent variables to only one. There is always only one dependent variable, target, right? Something that we're trying to predict. But we can do that on the basis of multiple, in general, predictors, independent variables. So simple linear regression essentially is a simplified view of the world. Remember the example that we discussed? It was about pricing the used car, right? So when you go to the dealers and you start browsing around, different cars, it can be the same thing, right? Ford Taurus, 3 years old. But they all have different prices. So why is that happening? Well, one of the most strong factors in pricing the car is the mileage. Of course, it's not the only factor, right? What also matters is how many accidents the car was in, maybe how many owners it changed, right? If it's too many owners, there may be something wrong with the car, right? People were trying to get rid of that. Why? There's something that's going on. Color can be the factor, number of extra features, right? So a lot of different things, the year of the car, a lot of different things can contribute. But we're taking the simplistic view and saying, all these things are important, but mileage is by far the most important. So let's see how far we can go by just considering the mileage as the only factor that predicts the price of the car. That's simplistic view of the world, of the real world. And that's simple linear regression. There is only one predictor. So in general, there are many variables that you may want to consider, obviously, right? So therefore, in this section, we're going to take a look at the multiple linear regression. And what we expect is, since you're creating a more sophisticated model of the world, you're including more than just one factor, right? Our model is expected to fit the data better, because you are looking at more dimensions, more different facets of the reality. You're saying that, for example, in the case of the car, mileage is not the only thing. If we include other factors, maybe our model will perform better, right? Maybe it will fit better to the data. So this percentage of unexplained variability, R squared tells you what percent of variability is explained by the variables that you've selected, right? So 1 minus R squared tells you how much of the variability in your target variable is still not explained. Well, that means that we're missing maybe something, right, from our model. And if we include that, our fit will be better, our square will improve. Okay? That's the idea behind the multiple regression. So the model in general will look like that. As always, we have only one single target variable, which is dependent variable y. But there are, so if I forget about these variables, beta 2x2, beta kxk, right? If I erase them from here, I'm going to go back to my good old friend, simple linear regression, right? But the fact that I have multiple predictors, x1, x2, xk, all I have to do really is to expand my equation. So just like what I had for the variable x1, I'm going to replicate the same form, and I'm going to say, well, add more linear terms to the equation. So x2, the other variable, is multiplied by its own slope, and that's another term in the equation. So all of them really form this linear relationship, right, with my predictor, with my target variable. So it looks like a straight line equation, but in case of multiple dimensions, right, multiple axes. So that's essentially how I'm going to try to find my model. Okay, every variable enters the relationship with my target in a linear fashion, multiplied by a constant, the slope. All right. Well, required conditions now are a little bit expanded actually. So same idea as I had for the simple linear regression. Number one is your error variable, epsilon. Let me move it right here, okay? The other way how we call the error variable is residual, right? So all of our residuals really are coming from this error variable distribution. That's what residuals are. Okay, the distribution of the residuals is normal. We had this condition for the simple linear regression, and it's still the case for the multiple regression. Nothing changed here. Okay, the mean residual is 0. What does that mean? That means that my average error that I'm making is 0. Sometimes I'm over predicting the target variable, sometimes I'm under predicting. So half of my errors must be positive, half of my errors must be negative, but on average I should stay on target, right? My average error should be 0. That's a natural requirement. Okay. Then number 3 is the standard deviation of error term is constant. In other words, I should see no expanding residuals, no contracting residuals, right? So we discussed that also for the simple regression. We said that your residual plot should look like a random cloud of points with uniform thickness, right? Residuals do not increase, the residuals do not decrease as I go, they stay about the same, okay? So that's my condition number 3. There should be no heteroskedasticity. So residual plot should look like a homoskedastic plot, right? The residuals should not reveal any curves, trends, or any recognizable patterns, right? So that's another test. All of these were applicable, all these 4 conditions were applicable to simple linear regression. But for multiple regression, we have one more, which we didn't have in the simple linear regression case. The variables x, my predictors, which I call independent variables, they should be truly independent from each other, okay? Not from the target variable. In fact, it's preferred that my independent variables are strongly correlated with target, right? That's what creates a good regression equation for me. The stronger my predictors are correlated with target, the better the model is going to be. But among themselves, they should be not correlated at all. So they should be truly independent. That's something that's called test for multicollinearity, and we're going to take a look at that in more details later, okay? All right. Now, without further ado, ladies and gents, let's give it a spin, okay? University admission. So let's kind of chit-chat about that first. A few years ago, I'm guessing a couple of years ago, all of you applied, right, to CNU, and you got this letter that says, yeah, congratulations, you're in. Anybody transferred to CNU? You transferred from where?
William and Mary.
William and Mary? Oh, okay. So what made you transfer?
I hated it.
You hated William and Mary?
I hated it.
Oh, wow.
It's what you would think. It's so, I mean, I like my academics, but it was so, everybody was just focused on that, and I just didn't want that.
Okay, so they concentrate on studies and
Yeah, I mean,
don't have much else
that's
going.
important, but it was just too high pressure.
Too high pressure environment. Okay, all right. Patrick, are you you just came here. Okay, Milan, you came here. Okay, all right. So when university, you can consider yourself as the part of the university admission office. Okay. Like at CNU, for example, how many students do we accept every year? Well, it's easy actually to compute. The university has 5,000 students, right? And these 5,000 students go through freshman, sophomore, senior, junior year. So approximately same number of people at any level, right? So we divide 5,000 by 4. That means that every year we graduate about 1,250 seniors, right? And to replace them, we need to accept about 1,250 freshmen, right? So the freshman class that is entering CNU should be on average 1,250. So that applies to any university, right? So you take, for example, UVA. UVA, I believe, the enrollment numbers are around 22,000 people. Undergraded, right? Undergraded. So we divide that by 4. So every year they accept about 5,000 300 or something like that students into their undergraduate program. Okay, so how many applications? Obviously, people that you accept are just a fraction of people who apply, right? How many applications does the university receive? Well, I don't know the exact numbers, but I heard that it's around 8,000 applications. CNU accepts around 8,000 applications every year. So,
Accepts.
receives, not accepts as in, come in and study with us, but receives about 8,000 applications. So, the admissions office has actually a tough job, right? How to pick people who receive an admission letter from these 8,000, okay? So, well, first of all, obviously we don't want students who will not perform well, right? So if we can spot early on students who will probably struggle with their classes and be, suspended eventually, and maybe even leave the college, right? I mean, we don't want them to have miserable time over here. So therefore, probably the students will get a rejection letter, right? So the idea basically is that students will perform well academically, and that primarily, how do you measure that? GPA, right? So anything above 2.0 is considered to be good academic standing at CNU, right? So if you're maintaining GPA 2.0 or higher, then you will just keep taking classes. But if you drop below 2.0, then you go on academic probation, right? I believe first semester that happens, you get a warning email, and the email will say, well, you did not maintain the required minimum GPA, so therefore you cannot enroll for 15 credit hours, right? That's what happens. You can enroll only to 14 and no more than that credit hours. So that means that you have to take, 4 classes, maybe 1 lab, or there is a course, it used to be called College 150, probably it still is, how to learn, how to, manage time, how to take notes, how to get help when you're writing a paper, these kind of things. And then when it happens second time, your GPA dives below 2.0, you go on academic suspension, I believe. For 1 semester, they're saying, okay, you don't seem to, still have a grip on the classes, so therefore you need to take a semester off and then come back. Okay. So university wants students to succeed, and that means they want students to achieve high GPAs. So maximization of GPA is the name of the game. Well, how can we predict who will achieve high GPA and who will not achieve high GPA? When you accept people, you don't know. It's because it's in the future, right? But there may be something in the past. We accepted students and they performed academically, high performance, medium, low, whatever it was. And at the moment when we accept students, when the university accepts students, they know a handful of things about them, right? All these things that students supply with their application. That being high school GPA, one of them, right? Then everybody takes SAT or ACT, so the score, how you performed on a standard test. Then there is a survey, right? A lot of people are required to write a survey or essay kind of thing, right? You get a topic, it can be anything really, and you just write your ideas, what you think about certain subject matter. So what probably they're looking at, the admission office, is your ability to express your ideas, on paper, right? How clearly you can communicate in writing. Grammar, obviously, right? So that you don't make obvious mistakes, punctuation signs, all these things, right? How well are you prepared for writing a paper? And then there are other things that a lot of universities consider, such as how active a person was in the extracurricular activities. In other words, it's great that you're attending classes, doing homework, and taking the exams, but it can be that if you express interest in some other things, right? You participate in clubs, organizations. Maybe you organized a club. Okay, you were an officer of a club, treasurer, secretary, a vice president of chess club and Earth Club and green team or something like that, right? that means that you, in general, are a curious person by nature, and therefore you probably will do better in the university. So, here is the idea, right? The admissions officer wants to develop a model which will allow to predict the university GPA, at the end of the junior year at the university, on a scale from 0 to 4, based on these three things. How high was GPA at high school? What was the SAT score? And also, that number is self-reported. How many hours, on average, a person spent in school, in high school, at the extracurricular activities. Okay? So now we have 4 variables, right? Out of them, GPA at university is the target. That's what I'm trying to predict, right? How well the student will perform if admitted to the university. And I'm doing that on the basis of things that I know at the time of application. These are the only things that I know, right? That I can know about their future performance. And I'm trying to see if these 3 things, GPA, high school, SAT, and activity hours, will predict for me how well that person, that individual will do in their studies, okay? All right, so here is the list of laundry list for us, right? What we need to do: develop a model, test overall model validity, then test individual variables, okay? Interpret the coefficients of the regression equation, kind of elaborate on how well, how nicely the model fits the data, and check all required conditions, and for a certain student, predict how well they will perform. All right, well, let's get started. So I'm going to switch over from slides into the file. All right, and the file is posted on Scholar in JUMP datasets. It's closer to the bottom. Right there it says GPA. So let's download and open the file GPA. This is probably one of the most fun topics in the entire class, quite honestly, because it allows you to be creative. And today we're going to look at another problem where you will see that creativity part, you can get really creative with regression models. Okay, so I'm going to open up the GPA file, and there it is. Okay. So first things first, let's build a model. In building the model, technically, where you click is not very different. In fact, it's almost exactly the same as in the case of simple linear regression. So we're going to follow same steps, really simple, okay? Fit model, or alternatively, you can go to Analyze menu and fit model from there. Same thing. So this one is a shortcut. I'm going to press that button. And y is my target variable, right? The dependent variable. So what am I trying to predict? University GPA, right? So therefore, that's my y. And the others are my x's, right? Independent variables or predictors. Now note that at the moment when I put my dependent variable y in the right place, immediately JUMP says personality. Personality is kind of the method of fitting the model into your data, right? It says that since your target variable is numerical, and how do we know? Well, here is the blue triangle right next door to the variable name, right? And I'm going to use a default method, which is standard least squares fit the straight line method, right? So our target is numerical, and immediately this is our default method. How do we estimate the model? And the other 3 variables I'm going to add to the model effects, and then I'm just going to click Run button, and that's it. This is my model. If I scroll down to the very end of my output window, where there is a part that says, this section that says parameter estimates. That essentially is my model. Okay, these are the estimates of the numerical slopes and the vertical intercept. So my model really, I can write it down. So I'm going to open up the notes, and I'm predicting university GPA. university GPA. And that is based on 0.98, that's my vertical intercept. 0.9877 actually, plus 0.4463 times high school GPA. So let's go back. 77 plus oh god, I forgot it already. 4463 times high school GPA. 4463 times high school GPA plus next one is going to be related to SAT, right? 0.001866 times SAT. 0018. Oh, it's more zeros actually, right? It's 3 zeros. 1866 times the SAT score. And plus the last variable that I have is activity hours, and that would be 0.0504 times the activity hours. 0.0504 times activity hours, HRS. And that, ladies and gentlemen, is my model, multiple regression model. Okay? So it's very easy to estimate using JUMP. Quite literally, it's done in 3 clicks. All right. So let's keep going down the laundry list, right? So we just developed a model. Test the overall model validity. Now this test is very similar to what we performed before. Now you remember what we tested in our previous example when we discussed, what did we discuss? The prices of cars, right? Based on the mileage. Here's what we tested. Just a reminder. We tested null hypothesis that my price, the slope for the price, for the mileage, I'm sorry. Mileage was our independent variable, right? So the slope for the mileage, the only variable that we had, can be set to 0. If that is the case, that means that you can essentially take out the mileage variable from the equation completely. Slope is 0, mileage, whatever it is multiplied by 0, that equals to 0, so therefore mileage has no contribution to the price of the car, and therefore the model is not significant statistically. And my alternative was that, no, the slope, beta 1, cannot be set to 0. This is what we tested for model significance, right? Well, the difference between my previous case, the simple linear regression, and what I have now, multiple linear regression, is that I have more than one slope, right? I have more than one predictor variable, so therefore here is my slope number 1, beta 1. Here is my slope number 2 right here, beta 2. And here is my slope number 3. Okay? So really, I should test more than just one slope. So therefore, my test that I'm performing actually expands now. Okay? So I don't just test beta 1 equal to 0, but I test them all. Okay? I'm going to say that I can set my first slope, second slope, and third slope, all of them simultaneously to 0, and the model will not suffer if I do that. Okay? Now, effectively, when I do that, when I set all the slopes to 0, I'm eliminating all my independent variables out of the equation, correct? I'm saying that now high school GPA is not an important variable, and SAT is not an important variable, and the activity hours is not an important variable, right? So therefore, none of the things that I'm considering are making any substantial statistical contributions to the university GPA. So therefore, my model essentially altogether is null and void, right? So therefore, model is not significant. That's my null. Okay? Now, alternative would be, it can be that my, for example, high school GPA is important, but everything else is not. Or it can be that SAT is important, but everything else is not. Or it can be that the only thing that's important is activity hours and SAT, but high school GPA doesn't make any contribution. Or maybe all four of them are important, right, and significant. I don't know. So therefore, here's how I'm going to write my alternative, that at least one of my slopes, beta I, is not equal to 0, where I can be 1, 2, or 3 in this case. Right? At least one slope has to stay non-zero in my model. Can be more than one, right? Can be 2 or all 3 of them, all of them. Right? But if at least one of them is statistically non-zero, that makes the model altogether, overall, is useful and significant. Okay? So this is what I'm testing for the overall model significance, ladies and gentlemen. Make sense? Any questions? All right, so let's go back to jump, and let's see where this p-value is. Okay? This p-value can be found right here, where it says analysis of variances. So ANOVA is actually used by regression equation in order to build the model and estimate if the model is significant. And my probability greater than f is the p-value for this specific test, right? So therefore my p-value is less than 0.0001. So what do I do with a small p-value? Always in statistics, if p-value is small, I reject the null, right? So p-value equals to 0.0001, less than 5%, which I'm using as a standard way to test hypothesis. So therefore reject the null in favor of alternative, and my alternative says that at least one of the variables has actually something to do with what I'm trying to predict, with my target, which is university GPA. Okay? Maybe not all the variables are useful, but at least one of them, they do contribute to the model. So that's how I test overall model significance. Okay? Now let's go back and let's go again, let's go further through our laundry list, right? How well does the model fit the data? So here I have to estimate the goodness of fit, right? I used to call it accuracy of the regression model. It's not quite accurate statement. I'm not measuring accuracy here. I'm really measuring, well, it's kind of the same thing. Goodness of fit. Goodness of fit, you can say, well, how closely I'm following the data, right? So accuracy in a sense. I'm measuring accuracy. Okay, so where in the output do I look? Summary of fit, right here, okay? And my primary indicator, how well the model fits the data, is going to be r squared, but note that I don't have just r squared anymore. I have another one, right? R squared adjusted, okay? In the simple linear regression in the previous model that we looked at, like when we predicted car prices based on the mileage, we had only one r squared, okay? And this r squared was actually the coefficient of correlation squared, as we discussed, right? You take your coefficient of correlation between your x and y, you square that, you get yourself r squared measure. That's what happens in case of simple linear regression. Okay? In case of multiple regression, things are a little bit more convoluted because you have multiple correlations going on, right? You have a correlation between your high school GPA and university GPA. You have a correlation between your SAT score and university GPA. You have a correlation between your activity hours and the university GPA. So you can't just square your correlation coefficients, add them together and say, hey, look, this is it. This is my r squared. So the formula behind this r squared is a little bit more sophisticated and convoluted. Okay? But that's my primary measure of how nicely the model fits the data. Okay? So if I'm using just my r squared, right now my r squared says 0.3939. So in other words, approximately 39.4% of the variability from student to student in terms of their university GPA is attributed to and explained by the variability of high school GPAs when they apply, SAT scores when they apply, and also activity hours spent at high school in extracurricular, whatever classes. Okay. So in other words, the three variables that I picked for my prediction, high school GPA, SAT score, and activity hours, they collectively explain about 39.4% of what happens in the university GPA data in terms of their variability, okay? So, is it a good model or is it a bad model? How nicely it fits the data? We discussed that R-squared, unfortunately, it has no critical numbers, right? Critical values. What we want R-squared to be is close to 1 as possible. In this case, you have nearly perfect model, right? If it's close to 0, that means that, well, your model sucks, okay? It does not explain a lot, and it doesn't do it well. So I'm kind of in between here, right? I'd say it's a decent model. It's not a super great model, but it's fairly decent. It explains about 40% of what's going on with my high school, with my university GPAs, right? So model is not that bad. But actually, let's do this. Instead of R-squared, let's use in multiple regression adjusted R-squared, okay? So for the simple linear regression, the only thing that you have is R-squared. Then we use it just straight as it's reported, okay? In case of multiple regression, instead of R-squared, let's use adjusted value. Now the question, of course, is what's the difference, right? Now you can see that there is not much difference between them, right? So R-squared is 0.39, your adjusted R-squared is 0.37, so they're very close. But what's really going on? What is the difference? Well, here is the funny part about multiple regression. The more variables you throw into the mix, that would be independent variables, right? The better your R-squared becomes. Even though some variables may have nothing to do with what you're trying to model, okay? For example, if to this model I'm going to add something about the students who apply that has no effect from the general, reasoning standpoint, has no effect on the university GPA, such as, for example, their height, okay? Student's height. How tall is the student? Does that really matter in terms of academic performance? No, it shouldn't, right? But what will happen if I add the student height into the mixture, my R-squared will go up. The more variables, the more independent variables I throw into the mixture, the higher my R-squared becomes. So essentially what I can do is cheat, right? I can throw in 150 additional variables to the mixture, okay? Every single one of them will improve my R-squared by a fraction, right? By like half a point or, 1/10 of a point, okay? Something like that. But if I throw 150 different variables at the model, from 39% R-squared, I'm going to go up to 95% R-squared, okay? I'm going to throw in everything. Student's height, student weight, their blood pressure, the vision, or something like that, okay? How far are they from home, all right? What's the mileage on their car, or something. Just, something that completely unrelated to the university academic performance. My R-squared will slowly but surely climb up. And I will end up in a situation where I'm going to stay at R-squared and say, wow, that's a great model. It has an R-squared of 95%. Awesome, right? But in actuality, what I did, I cheated, right? I added a bunch of variables that have nothing to do from the general standpoint with academic performance. Now, statisticians, therefore, to avoid that overfitting, okay, that's what is called in statistics overfitting. In other words, I'm trying artificially to boost my model performance by adding more and more and more variables, right? I may get a great performance indicators, but really my model is not improving because I'm not predicting anything, right? I'm just throwing random stuff, hoping to improve the R-squared. That's all. So statisticians came up with R-squared adjusted in order to punish for adding unnecessary variables. That's essentially what happens, okay? So if I start adding more variables into the mixture, my R-squared will go up, but my adjusted R-squared will actually go down. And that's the way how statisticians kind of, in a sense, they censor themselves, right? So in order to avoid model to become overly complicated and overfitted, when I'm starting to pick up on the noise, and I'm starting to throw in variables that have nothing to do with what I'm trying to model, R squared adjusted will take a dive. Okay, so even though my R squared can still climb up, adjusted will say, hey, you're not adding any value to the model. You're really adding junk variables, right, that have nothing to do with your university GPA. Okay, so it will start punishing me for adding unnecessary, unrelated variables. Right. So therefore, instead of R squared for the multiple regression, we're going to use adjusted R squared. It's kind of a way to put a put a cap. Oopsie, hold on, let me log in. Oops. So essentially, this is a mechanism how statisticians keep things in check, right? In order to not overly complicate the model and leave only variables that are really important, that really matter. Okay? Make sense? So we're going to use just R squared, bottom line. All right. So that was a long explanation of how well the model fits the data. Interpret the coefficients for each interpret each coefficient of the regression equation. Okay, so let's go back to the regression equation. So I have to provide a plain English interpretation of my coefficients. All right. So let's start with high school GPA, right? This one. So standard interpretation is every time when you increase the independent variable by 1 and keep others the same, unchanged, the slope then is how much your target variable is being affected. So specifically, if I increase high school GPA by 1 and keep other variables intact, so SAT and activity hours remain unchanged, then what kind of effect will I have on the GPA? Well, it appears that high school GPA goes up, everything else stays the same. Your end of the junior year university GPA is expected to rise, because it's a positive sign, right, by 0.4463. So every point of increase in high school GPA results in 0.4463 increase in the university GPA, on average, right? That, of course, is not exact match for every student, but if I take hundreds and thousands of them, everybody will be affected differently. On average, that's going to be the effect, okay? SAT, same thing, right? If I increase the SAT score by 1 point and everything else is unaffected, high school GPA remains the same and activity hours remain the same. And impact on your junior year university GPA is going to be positive 0.001866. So almost no impact, right? Very small. So therefore I can actually say, well, how about that? If, for example, a student prepares for SAT, right, really hard, bless you. They take a course, they study more, etc., and they improve the performance on SAT by 100 points. Then what kind of impact will I have? And high school GPA and activity hours, they have no changes, right, remain the same. Well, I have to multiply this increase by 0.001866, and the answer is going to be 0.01866, okay? So you improve your SAT score by 100 points, your GPA goes up by about 0.02. Now, informally speaking, is that a huge impact on GPA? No. So therefore, what do you think? SAT, is it a strong predictor of performance in university? Probably not, right? Because we just saw from the model. It goes up by 100 points, SAT score, GPA barely feels it, right? It's only like 0.02 effect on your university GPA. So, informally speaking, I'm thinking that maybe SAT, individually, this variable, is not a great contributor to the model, right? Because its impact is not huge, okay? All right, so now I'm going to erase that thing. Okay. And finally, let's interpret the activity hours. Very similar, right? If you increase activity hours by 1 and remain high school GPA the same and SAT score the same, then your impact on the university GPA is going to be 0.0504. Okay? That's my plain English interpretation of slopes 1, 2, and 3 of my model. Increase the independent variable by 1 unit and keep the rest the same. The slope will tell you how much impact you will see in the target variable, university GPA. Okay? All right, let's go back. So we're done with this part. For each variable, test the significance of this variable for the model. Now, here comes the fancy part. Sort of. All right. Well, first of all, let me point out that about 5-10 minutes ago, we tested the overall validity of the model, right? This was our test. Before running anything else, we said, let's see if this model is significant in general, overall, as the whole, or not. Okay, because if I find that null is true, and this is it, I'm done, right? I'm testing this first hypothesis and I find that my p-value is high and the null is true. That's it. After that, I can take my null, I can take my variable 1, 2, 3, multiply them by zeros, no effect on the university GPA. So therefore, I don't have a model essentially. What I have really is just a constant, right? The intercept. That's it. So doesn't matter what high school GPA you had, SAT score, no effect on university GPA. Okay, so this is the first model that we tested. Now we're going to test each variable individually. So here's what I'm going to test. For the variable, what was the first variable? High school GPA, right? Oops. For the variable high school GPA, I'm going to test this hypothesis. Now is that the slope for the high school GPA alone, not gap GPA, GPA can be set to 0. If I do that, essentially, that means that high school GPA is not a significant variable, agree? If slope is 0, whatever GPA in high school you multiply by 0, it's 0, it has no effect on university GPA, right? So therefore, if I find in favor of null, I'm going to say that high school GPA is not a significant variable. Okay? And the alternative, of course, is opposite, right? That I cannot take slope for the high school GPA and set it to 0. So it's essentially staying what it is currently in the equation without any changes, right? I cannot replace it with 0 and hope for just as good of a model. It's going to suffer, right? Where do I find the p-value for these tests? Every time when you have a test, you need a p-value, right? So let's go back to the jump output right here. And the p-values for these tests are found in the same exact spot or section where the estimates of the slopes and intercepts are. Okay, right here, parameter estimates. This column we used as an in order to build the regression equation. Right, you can see that the very last column that says probability greater than t, that's where your p-values are located. Okay, so since I'm testing high school GPA, I have to look on the same line, and here is my p-value. Does not report the p-value. Well, actually it does. If you leave it long enough, it will show your tooltip. I don't know, it doesn't want to show me anything right now. Typically it will show you like large, oh, here it is. P-value is 1.63 E minus 6. What does that mean, E minus 6? Have you ever seen anything quite like that? 10 to the negative 6, right? So my p-value is 1.6 times 10 to the minus 6th power, which means that this is a really, really small number, right? It's like 1 millionth or 2 millionths, right? That's my p-value. Okay, so I'm going to go back to my notes and say p-value is very small, definitely smaller than 1%. So therefore, what do? Reject the null in favor of alternative. And what does my alternative say about my variable high school GPA? Is that an important variable or not important? It is important, right? Because it has to stay the way it is. So high school GPA is a significant variable. That's good, right? And I have to do the same test for the rest of my independent predictors. So therefore, let's draw the line right here. And the next one that I'm going to test was SAT. Now, you remember what we did for SAT in the previous couple of slides that we looked at. We said SAT does not have a gigantic impact on GPA, right? Even increasing SAT by 100 points doesn't seem like it will create huge splash on the university GPA. So therefore, my hunch right now would be that SAT maybe is not an important variable, right? Because it has no huge impact. But I'm going to test exactly the same pair of hypotheses. So my null is going to be that the slope for the SAT score can be replaced with 0, making SAT not a significant variable, right? And my alternative is going to be that no, whatever slope for the SAT is, I cannot replace it with 0. And therefore, SAT is an important variable. It's essential and significant for the model. Well, let's go back to JUMP. And I do the same thing, right? Here is my SAT coefficient, and at the end, here is my p-value. So what do we see? 0.5652. So my p-value here, 0.5652. And I can see that p-value is high, right? It's higher than anything that I can use reasonably, realistically for hypothesis testing. That would be 10%. High p-value means I fail to reject the null, right? So therefore, I keep the null. And what does my null say? My null says that if I replace the slope for the SAT variable in the model with 0, model will not suffer greatly. Okay, so therefore, SAT, I'm going to write it, SAT is not a significant, statistically significant variable. Okay? So that's kind of a way for us to discriminate between variables that actually do contribute to the model and variables that have pretty much nothing to do with what we're trying to estimate, to model. Okay? So now let's test the last one, right? Or what was that? Activity hours, right? Activity HRS. So same thing, right? My null is going to be that I can take the slope for activity hours and set it to 0, making variable not relevant. And alternatively is no, activity hours slope has to stay non-zero, whatever it is right now. So I go back to JUMP, and what do I see for activity hours? 0.0083. That's my p-value. So p-value 0.0083, and it's less than 1%, right? Less than 0.01. So if p-value is small, I reject the null in favor of alternative, and my alternative says that this is a significant variable. So what I found is, out of these three variables, three independent predictors, well, I think they're independent right now. I don't know yet. Three predictors. High school GPA is significant. Activity hours are significant. But SAT, we can get rid of that and the model will not suffer greatly, right? So this variable essentially is useless. Okay, make sense? Okay. Now let's actually take a look. This is kind of an informal way to test if the variable is making a contribution or not. We said that SAT, if we get rid of SAT, the model will not suffer tremendously. What do I expect with R squared to happen? Remember we discussed that. If you add things to the model, R squared goes up. Whether they're useful or useless, you throw in additional independent variable to the model, R squared has nowhere else to go but up, right? It may go up only slightly, but it will go up, regardless of what variable do you have, useful or useless. Well, let's take a look. On my output window in JUMP, there is a portion that says, section that says effect summary. Do you see that one? What I'm going to do is remove the SAT variable from the model. How do I do that? Click on the SAT and click on the button remove. But before I do that, let's take a note. My R squared is 0.3939 and my adjusted R squared is 0.3749, right? So click on the SAT and click on the button remove. What happened with my R squared? It was 0.3939. I removed the variable which we already tested and found insignificant, right? What happened with R squared? It went down, right? From 0.3939, it went down slightly to 0.3918. Did the model goodness of fit suffer a lot? Nope. It went down by 0.002 or 0.02, right? Went down only by 2%. So therefore, goodness of fit did not suffer tremendously. That is another informal way to see that your variable was not significant, right? And at the same time, what happened with R squared adjusted? What was it before? Do you remember? Let me add the variable back. I'm going to add the SAT. And my adjusted R squared was 0.3749. Now I remove SAT, and my adjusted is 0.3792. What happened to the adjusted? It increased slightly, okay? Remember we discussed what adjusted R squared does. If you add a variable that's not important, it punishes you by driving the value down, right? Now we removed the useless variable. It actually rewarded us, right, by saying, yep, now your model, it's actually a better fit because you got rid of the insignificant, insufficient variable, right? So they kind of moved in the opposite direction, right? R squared went down because you removed the predictor, but adjusted R squared said, yeah, but you removed an important predictor. So therefore, I'm going to reward you for that, okay? Your accuracy now is better, okay? Make sense? All right. Now, what else do we need to take a look at? Let's take a look at required conditions first. Okay? Let's take a look at if anything is violated. So, number one, what do we have to test? We have to test that residuals are normal or not, right? Well, we did that before. I told you that unfortunately, JUMP does not provide us with the normality plot by default. So we have to save residuals and then look at them, right? So, from the red triangle menu, I'm going to say save columns. We did that before in the simple linear regression case, so it's the same. Save residuals, right? I'm going to save residuals. The residuals go back into my original data table. So I'm going to have to switch back to the original data table, just like that. So this is my additional column with residuals that was just created. Now I'm going to see the distribution of this thing. So let's look at the distribution. All right. And here it is. Let's stack it. Looks bimodal, right? But I'm thinking this is a random flick. Other than this, value that I have, it all looks nice, bell-shaped and whatnot, right? So let's take a look at the quantile plot, normal quantile plot. Looks nearly darn ideal, right? Very closely follows the diagonal straight line. So I think that my residuals are actually normal. Well, to be formal about that, let's go ahead and fit continuous normal distribution. And here, test the goodness of fit, just like we did many, many, many times already, okay? So Shapiro will test as that my p-value is 0.1479. So high p-value, right? Well, high relative to 10% significance, or 5%, or 1%, any of them. And it says you're testing null that the data are normal. Well, with high p-value, I fail to reject null, so data are normal, right? Statistically normal. So that one checks out, okay? In this problem, my residuals are normally distributed. That is good. Now let's go back to the output, and let's take a look at the residuals plot. Okay? What are we looking for? Few things. Number one is your average residual must be 0, right? In other words, the residuals, some of them are positive. That's when you underpredict. Your actual data is higher than your prediction. Some residuals are negative. That's when you overpredict. When your actual data is lower than your prediction, therefore difference is negative, right? But on average, my residuals should be at 0. So here's my average line, the blue line. It says pretty darn close to 0. So that one is checked. Another thing that I have to look for is all kinds of patterns, right? Any pattern, any recognizable, identifiable pattern is bad, okay? So what do I see? I see that it's a random cloud of points, right, first of all. So the residuals do not increase systematically, do not decrease systematically. They stay about the same, right? Same uniform thickness, pretty much universally all across, right? There are no easily, obviously identifiable patterns, no weird things, trends, curves, lines, nothing quite like that, right? So this is a well-behaved residual plot. So I declare that this part is okay. Now, the last thing, remember I promised you when we just started discussing, when was that? Let's go back. And we just started discussing required conditions. So these, we just checked. Normality, the average is 0. Standard deviation of error variable is constant. That means that it's uniform thickness. It's not going up or down. And residuals do not reveal any patterns. That was the standard stuff that we did with our simple regression, right? This is extra. The variables must be independent from each other. Okay? Remember that X variables, predictors, the other name for them is independent variables. Independent from what? From each other. They should be related closely, I hope, with my target, with what I'm predicting, dependent variable, right? So their correlation of coefficient of correlation should be high. But among themselves, they should be disconnected, right? That would be nice. Because what happens if they're connected? You change one of them, another follows, right? So they're not exactly independent. They're kind of hooked up together. How do we estimate if they are correlated or not? Here is the standard way how we're going to do that. I'm going to go create cross-correlation between all of my independent variables, right? So I'm going to the menu Analyze, y'all. Okay. Then multivariate methods, and pick this one, multivariate option. That will create a matrix of correlation, coefficients of correlation for me. Okay, so multivariate option, and first of all, here I'm testing only independent variables, right? So I'm not going to even pick up the university GPA. I'm going to leave it alone. High school GPA, SAT, and activity hours. So my predictors, allegedly independent variables. I'm going to put them in the columns area, all three of them, and click on the OK button, and that will create for me this output. So let's examine that. On the top of this window, you will see the matrix consisting of all cross-correlation coefficients. Okay? Every variable with every other variable, and with itself also. So for example, high school GPA and high school GPA with itself, perfectly correlated. That's true for any variable. Any variable is perfectly correlated with itself, right? I'm 5'7", I'm 5'7". Bam, it's a point on the straight line, right? Patrick is, how tall are you, Patrick? 6'5". Wow, he's much taller. 6.0, right? Okay.
I thought you said 6'5".
Okay, so Patrick is 6, and he's 6, right? It's a point on the straight line. So it's a perfect correlation, a variable with itself. So therefore, that's not an interesting case. Therefore, variable with itself, you can see there is nothing going on, right? At the same time, these are cross correlations between variables. Okay, so JUMP, as you can see, by default gives you something that's called correlation ellipse, right? What is it? It's basically an ellipse that covers about 95% of the points. Okay, so it's a shape that tells you how strongly the variables are correlated with each other. If the shape is round, that means that pretty much nothing that's going on, right? Correlation is close to 0. The closer the shape to the straight line, the more narrow the ellipse is, the more it's aligned along the diagonal, the closer the correlation to +1 or -1, which are both perfect cases, right? So, what can we see? Just judging by these pictures, right? This is almost a perfect round shape. So, therefore, high school, GPA, and SAT have no correlation. And here's the confirmation right there in the correlation matrix, okay? That says high school GPA and SAT very close to 0. That's good, right? They are independent. High school GPA changes, SAT no effect. Same thing with SAT. SAT has nothing to do with high school GPA. So they are truly independent. And this one is also very close to circle, right? That is SAT with activity hours. And you can see that also from the correlation matrix. Minus 0.0337. Very close to 0. No correlation here, okay? That one is more of a line, less of a circle, right? So here we can expect higher correlation. And in DD, 0.49. Now remember when we discussed the informal way how to classify correlations. What did we say? If your correlation coefficient, let's kind of recap this part, right? If your correlation coefficient, absolute value, if your absolute value of coefficient of correlation is between 0.7 and 1, so if it's close to +1 or -1, then we're going to call that strong correlation, right? If your R squared absolute value is between 0.3 and 0.7, how do we call that case? Not strong, but medium. And if you are close to 0, if absolute value is between 0 and 0.3, then we're going to call it weak. Okay? So in other words, in order for us to find out if something is highly or strongly correlated, we should be on the lookout for either high positive values or high negative values, right? More than 0.7 or less than -0.7. All right. So here we have 0.4942. Is that a strong correlation? Nope. It's medium, right? They're kind of okay correlated, not highly, not very strongly. So therefore, what do we say? Are these independent or not? They are independent, right? More or less. So when it's 0.7 or more, then we're going to say, wow, that's a strong correlation. They're really highly, there is a friendship going on here. Right? One goes up, another goes up. One goes, or maybe other way around, right? One variable increases, another variable decreases strongly, right? Correlated. But 0.4942 is not quite there. Okay, so we're going to say that there is no strong correlation, and therefore there is no multicollinearity. So the scientific term, statistical term, and I had a slide on that actually, somewhere closer to the end. Statistical term for that is called multicollinearity. Bless you. Okay, so multicollinearity is a bad condition. It happens when some of your independent variables are highly correlated with each other. That's an undesirable situation to have. Okay, so that means that essentially that your variables, both of them, tell you the same story because you increase one, another is strongly affected. They move together, right? They're not disconnected. Okay, and they should be disconnected. So if two variables are highly correlated, then probably they should not be simultaneously present in the model because essentially you're kind of duplicating the same variable almost, right? So that's why multicollinearity is a bad condition and can lead to weird effects. In fact, today I'm going to assign you a homework where hint hint, wink wink, you will have some weird effects, okay? That will be hard to explain. So you will have to check the required conditions and see if you maybe can spot why exactly you have weird stuff going on with your model. Okay? All right. So the last piece of the puzzle is using the regression, right? So let's do that. Okay, hold on. What was the last question that we did not address? This one, right? Suppose you have a high school student who applied to the university. So they have university GPA, high school GPA of 3.3, SAT score of 1200, and 2 weeks in extracurricular activities. Should we accept this student or should we not accept? That's the decision that the admissions office has to make, right? So in other words, we have to predict how well that person will perform at the university, right? So let's go ahead and use, on the level of how do you use the model, it's really straightforward, right? All you have to do is say his university GPA is going to be whatever 0.9877, our vertical intercept, right, plus, oh God, I can't remember what were the coefficients. Let's see, let's go back. This one, right? I need to put back the SAT, right? So I'm going to add the SAT back into the model, assuming that it's relevant. We know that it's not, but I'm going to keep it anyway for now. 0.4463. So 0.4463 times their high school GPA, which was 3.3, right? Yeah. Plus 0.001866, that's the slope for SAT, times his SAT score, which is 1200. Plus, I believe for the activity hours it was 0.0504, that's an ugly 5, times, 2 hours, right, of activities. So it's just a matter of plugging in the values and calculating the result. Or you can use JUMP. JUMP is a nice tool to provide all kinds of utilities for us. So factor profiling, profiler. And here is basically 3 graphs, right? How all 3 different variables, x1, x2, x3, affect the GPA. So first one, I say the high school GPA. I just replace it with 3.3. You can see that the SAT line is almost flat, right? The SAT line is almost flat. And we saw that this is not a significant variable to begin with, and the slope is very low. That's the reason. So I replace the value with 1200. And then activity hours is 2. And that's your answer. So if you accept that student to the university, then by the end of their junior year, you can anticipate the average of 2.7856. Now, of course, this is where your model ends, right? That's it. We built a model, we used the model, we assessed how nicely it fits, which variables are important, which are not important, right? All these things, we did diagnostics. Now, the next question, of course, this is where statistics ends, right? The next is, well, here, admissions office, that's a model, now use it. So they take a student, right? This is one of the high school students who applied to them. They said, here's my SAT, high school GPA, everything. I calculate the GPA, turns out to be the predicted value 2.78. What's my next action? It's a binary decision, right? Do I accept or do I not accept? So from this, from the office standpoint, you should decide on your cutoff, essentially, right? They're saying, hey, let's calculate the GPAs for every student that we accept or reject, right? Everybody. All applicants, let's run them through this model. The model spits out the GPA for us, predicted university GPA. Let's rank them from highest to lowest, okay? And let's after that decide where the cutoff is going to be, okay? And that's probably the reason why universities, every time when you apply to the university, you want to know how high do I need to score to get in, right? That's the all-important question. Do a lot of them tell you how high? No, they don't, right? They tell you, remember we discussed that at the beginning of the semester, they put summaries, right? They say, 50th percentile interquartile range of SAT scores was between this and this. They don't say, if you score at least 50 on your SAT, we'll accept you, right? They don't say anything like that. Why? Because of this, okay? Every year, when they receive applications, they run this type of model, and they get different results from year to year, right? Let's say they know that out of 8,000 applications, they need to accept, say for example, 5,000 students, because 3,500 will turn them down eventually, and about 1,500 will get they get an acceptance, and then after that, some of them will drop out anyway later on, right? So they know that they need to accept, let's say, 5,000 students. They need to send 5,000 acceptance letters, right? But every time when they run this analysis, they get different sets of predicted GPAs, right? So therefore, the cutoff point is different from year to year, essentially, okay? They know that, hey, top students who score, let's say, 5,000 top applicants, we're going to accept them right now and send them letter of admissions. But they don't know where the cutoff is going to be, right? From year to year, it's different. That's why universities do not publish this data, because simply they have no idea themselves how this year's applicant pool is going to look like, right? But that's definitely helping, right? You're essentially, this is a decision tool. You're not making the decision in the blind, well, this person looks nice, let's accept them, right? It's not a gut level feeling, it's kind of a numerical based system now. Make sense? All right, do you want to take a break? It's been a long streak, right? Okay, so now let me show you a few fun data sets, okay, that are provided with JUMP. Statisticians basically in the last century, well, statistics is about 350-year-old science, right? In development still. But in the 20th century, statisticians, as they started to get all these techniques and methods developed, they got into the mindset, for example, for regression analysis, that numbers trump anything. So once you get your model, if the model is fitting nicely, the data set, if you have a decently valued R squared, that's the only thing that matters. That means that you have yourself a good model. Well, there was a gentleman, actually a French statistician, named Francis Anscombe. In 1970s, he published a paper, and the point of this paper was to demonstrate that numbers are not everything. Okay, so let's do this. In JUMP actually comes with a lot of built-in data sets. Okay, in JUMP, I'm going to go to Help and Sample Data Library. There's an option on the menu, Sample Data Library. So here are all the files that JUMP comes with, right? And one of the files is supposed to read Anscombe. Do you see that file? Anscombe, right there. So I'm going to open up this file, all right? So in this paper that he published in the 1970s, he discussed 4 different data sets. And you can see that we have 8 columns, x1, y1, x2, y2, etc., etc. So let's start building simple linear regressions with each one of these pairs, right? So let's start with x1, y1. I'm going to assume, well, x is my independent variable, y is my dependent variable, obviously, right? So I'm going to go fit model, and my y1 is the y, and x1 is the effect. And when I run the model, it looks very nice, right? For example, this is my scatter plot. The very first graph that I see is the scatter plot. Okay? It looks like, in general, I have a bunch of points with a trend line fit into them. Correct? All right. So if I look at my residuals plot, what do you think about this residuals plot? Is it good? Yep. Looks beautiful, right? Random, no lines, no trends, no heteroscedasticity. Beautiful. Okay, so my R squared is 0.666. Is it decent R squared? Pretty decent, right? It says that 66%, almost 67% of your variable y1 is explained by variable x1. Okay, very decent value. And the regression equation is, let's write that down. Here's my intercept, that is 3, right? And 0.5 is my slope, correct? So therefore, I'm going to write down the regression. My y1 equals to 3 plus 0.5 times x1, right? That's my first regression, okay? So no issues with this model, right? Okay, I'm going to put that thing down, and I'm going to run another model, now with my x2 and y2. So fit model, I take my y2 and my x2 and I run the model. Oopsie. What do you see on the scatter plot? The points actually form very nice line, right? Very smooth line. Is it a straight line? Nope. So these are my points. Okay. What do they look like to you, by the way?
Almost a parabola.
Almost like a parabola, right? Quadratic equation. Okay. So you square x2, you'll get that shape, right? Okay. So here is your residual plot. What do you see? Clearly we see a parabola, right? So that's a problem because residuals plot should show you no patterns at all. And this is clearly a pattern, right? So therefore, relationship between x2 and y2 is not linear. It's actually quadratic probably, right? But how is the fit? R squared. Exactly same, 0.66, okay? How is your line? Exactly same. y2 equals to 3 plus 0.5 times x2, right? Exactly same coefficients, okay? Completely different data, pretty much crappy fit, right? Because obviously you're trying to fit a straight line into what looks very clearly like a quadratic curve, right? But numerically, like if we didn't see that picture, we would say, wow, beautiful, right? Same equation, same R squared, just as good as the previous model, okay? Now let's take a look at the third pair of things. So I'm going to fit yet another one. I'm going to pick y3 and x3 and run the model. Okay, that one is even funnier actually. What do you see on the scatter plot? Can you see that these the dots actually form perfect straight line, right? With the exception of that one. How do we call that kind of thing? That looks a lot different from the rest of outlier, right? You probably have an outlier, right? If you exclude that point, you will have nearly perfect relationship, but it's not because this point kind of tilts the least squares equation towards itself, right? So therefore, on your residuals plot, that's going to show up obviously, right? So all of your, if you look at the outliers, at the residuals, right? Here the residuals are positive because you underpredict. Here the residuals are negative because you overpredict, right? Your actual data is less than the straight line. And here there is a huge positive residual, right? So therefore, here's your plot where you can clearly see the pattern. But how about the fit? Same, 0.66 R squared and the same equation, right? Your y intercept is 3 and your x slope is 0.5, okay? And let's do yet another one, the last pair. So again, I fit the model and I pick y4 as my dependent variable and x4 as my independent variable. Okay, even worse, right? So what do we see? We see a bunch of x's, right, which are equal to 8, 8, 8, all of them, except for one x, which is equal to, looks like 19, right, this point right there. X is 19, yes, and y is also very different, right, 12.5, okay, right here, okay? So, what will happen if I exclude that point? I will have no regression at all, right? Because all of my x's are the same and all of my y's are all over the place, right? So x really cannot predict y, right? Because for one x you have a bunch of different y's. And once I have this point, it actually immediately says, that's it, I'm taking up the line. So the line has to contain that point, okay? This point in statistics is also called influential observation, okay? Another good illustration of that could be like this. Let's say I have a bunch of points, so here is my x and here is my y, okay, x and y. So let's say I have a bunch of points right here, and they look like a random cloud with no trends or lines or anything quite like that, okay? So if I have this type of data set, is it a good candidate for the linear regression? not really, right? Because it does not look like X can predict Y, right? Because any line that I try to fit into this thing, it can go like that, right? Oops. Or it can go like that. Or it can go like that. It's going to be just as good of a fit. Agree? Because it's really a cloud of points, right? It has no direction. Looks like a sphere, right? But suppose I have one point right over here. Guess what will happen? Immediately, the regression line will get a sense of direction. Okay? So it will go to this single point. So what used to be just a random cloud with no sense of direction at all, once you get a severe outlier somewhere out there, that thing immediately attracts the least square regression line. Okay, so therefore, here in the cloud of points, you can have hundreds of points, but and have no valid equation. Okay, no correlation going on. But once you have one point out there somewhere, then immediately your straight line, becomes fixed on that point. So therefore, this is called influential observation. Influential observation. And that obviously is not a healthy way to do the regression, right? Because one point cannot define the regression, but it looks like that's what it does in this specific case, right? So this is kind of similar to what we have right here. Agree? We have a bunch of points with no sense of direction, and then there is one point out there, outlier far away, which immediately defines your entire line, right? So clearly your regression, although your residuals, they look weird, right? Bunch of residuals here, and then there is 0 far away because it contains exactly the line contains exactly the point. And how good is the fit? Same thing. R squared is 0.66, and your regression is the same line, 3 plus 0.5 times x4. Okay, so we have 4 data sets, very different, right? Only the first one looks like a legitimate linear regression, right? Everything else looks just weird. Okay, but if you adopt this mindset that it's not important to look at the data, then you will never catch that, hey, data set number 2, 3, and 4 really are not a good candidates for the modeling as the regression equation, right? So therefore, the point of this gentleman's publication was to inform the statistical community that graphs, while a lot of people may view them as subjective way to evaluate the data and predict how well the model you're going to build, you have to start your analysis with graphing the data and looking at that, okay? Because that can tell you a whole lot about your future model, and if you need to make any adjustments to your variables, right? So just running the numbers, R squared and the equations and stuff like that, can give you a result, obviously, right? But how good and how usable the results are going to be is highly dependent on how your data is shaped. And that can be judged only by graphing the data and looking at the data. So this gentleman early on, back in 1970s, was trying to emphasize the importance of data visualization. Before you start running models, you need to look how your data is shaped. Okay, is there a model? Is there a good model? All right. So that's something that I wanted to emphasize. That before we do anything, we need to look at the data and see if this is really a good fit. Now, with that in mind, actually, I don't do anything just for the heck of it. I have a point. At least I try to have a point every time when I do that. Okay. So let's go ahead and do another problem, which I included at the end of this slide deck. Multicollinearity, university GPA, here. Variables transformation, okay? This is where the power of regression analysis can really shine through, right? Regression analysis is very powerful because, what we learned is just linear portion, right? We can create from that non-linear regression, try to fit the data better and better and better. So let's take a look at the following problem. In trying to find a new location for the restaurant, fast food chains like McDonald's and Wendy's usually consider a number of factors. Suppose that an analyst working for a fast food company has been asked to construct a regression model that will predict, to identify which new locations are good, probably going to be profitable, and which not so good, not so profitable. The analyst knows that fast food restaurants, they attract only a specific type of customers, right? Specifically middle-income adults and, of course, kids, right? McDonald's has this whole, do they still employ this clown thing, image, like this Ronald McDonald clown, right? And they have these playgrounds inside, right? So therefore, children is part of their marketing, right? It's a fast food for kids, okay? So particularly kids between ages 5 and 12. So here is what this gentleman does, the analyst, okay? In order to build a model to predict the restaurant profitability, he takes 25 areas and randomly where the restaurants were built, and for each area is approximately same in size, 5,000 households, okay, and has one McDonald's in it, fast food restaurant. So what he recorded for each place is gross sales in the previous year in terms of thousands of dollars. Also mean annual household income in the area, so how rich is the neighborhood, right, where the restaurant is being built, and also the average age of children living in the neighborhood. So these are available through census, okay? All right, so what kind of model can we build based on that? Let's go back to the data sets on Scholar and open up McDonald's data set. So there it is, right here. So 25 different areas, right? So let's take a look at the first one. In the first area, what he looked at, McDonald's restaurant ran what? $1,128,000 in sales in the previous year, right? In the area, in the neighborhood, the mean household income was $23,500 and the average age of kids was 10.5 among all the kids living in the area, right? So, and there are 25 of them. All right, so obviously I'm dealing with multiple regression, right? There is one target, which is what, by the way? What's my target? Dependent variable that I'm trying to model. Oh, there are 3 of them. One's supposed to be target, right? Which one? The revenue, right? How much money the restaurant generated in sales. And everything else is dependent variable, right? Income of people living in the neighborhood and also how old are the kids there. All right, let me just go ahead and run the linear regression. Multiple linear regression. Multiple because I have 2 predictors, right? So revenue serves as the target, y, and the other 2 model effects. So I'm going to run this thing, okay? All right, well, first of all, let's take a look at the scatter plot. So on the scatter plot, I have all the points, right? Predicted revenue versus actual revenue. Do you see any patterns just by looking at the scatter plot? Kind of hard to tell right now, right? So let's leave it alone for the time being. Let's go straight to the diagnostics, right? How good of the model is that? So my R squared, and we decided to use adjusted R squared, right? So my R squared is 32%, my adjusted R squared is 26%, okay? So in other words, about 26% of the variability in profit from restaurant, not profit, sales, right? Sales, revenues. Variability of revenues from one fast food location to another fast food location is because different locations have different average household incomes and different kids' ages, right? Average kids' ages. Okay. Now, let's take a look at the regression. What do you think? Not regression, sorry, residuals. What do you think about residuals? Do they look nice or not so much? Do you see any patterns, lines, curves, anything quite like that? Now here is what I see, okay? Here, the residuals these three residuals are kind of negative, right? There are no positives. Then they all become largely positive after that, right? With just a few under the curve. And then here, they all become negatives again, okay? So there is kind of a line going on like that, a curve, right? And the same curve I can probably see, so it's essentially the same thing, only expanded, right? If you look at the actual sales versus predicted sales, you can kind of see the same thing, right? It looks like the line goes from here all the way up, and then peaks, and then goes down, like that, right? Well, to see things even better, there are actually two other residual plots right here, okay? You can see that, right? This is a residual plot, it's called leverage plot, right? And they're also given by default. So what's the difference? Difference really is that this residual plot that we use so far is the plot of residuals versus predicted revenue, versus predicted value, okay? So for each restaurant, I predict what the revenue is going to be, and then I calculate the residuals, difference between the actual minus predicted, and I plot that, okay? So I can see that as the predicted revenue is getting higher, and I have more variability, and also residuals become kind of predominantly negative, right? But this is the same plot where the x actually is your variable number 1, x1, mean household income, and x2, mean average of kid, average age of kids, right? And here I can also clearly see the pattern, right? So for example, for the low median income, my residuals are negative with no positives, right? At all. And then they become positive with almost no negatives, and then they become negatives again, right? So in other words, I can see the pattern like that, okay? So it almost looks like a parabola, like in the previous case that we looked at in the Anscombe data set, right? Same thing happens over here pretty much, right? All the residuals are negative for low mean age of children, right? And then they become all positive, and then they kind of flatten out, okay? So in other words, here's what I'm thinking. Because residuals display this weird parabola-shaped behavior, my linear regression may not be a great fit, okay? I mean, linear can probably stay. There is a linear part to the whole thing, right? Because if I look at the if I test every single one of my independent variables, right? What am I looking for in order for the variable to stay significant? High p-value or low p-value? Remember what we're testing? Here's what we're testing. Let's go back to the notes. Here's what I'm testing, right? I'm testing every time when I evaluate the variable, my null is that the slope is 0, which means that the variable is not significant, and my alternative is slope is not 0, which means the variable has to stay, right? So for the variable to stay, do I need a p-value or high p-value, a low p-value or high p-value? I need to reject the null, right, in favor of alternative. Then the variable is significant. So I reject the null when p-value is low, right? So when I'm evaluating my variables, kind of judging are they useful or are they useless, I'm looking for low p-values, right? Because every time when I see high p-value for the hypothesis test, I have to stay with null, and null says you can take it out, model is not going to suffer a lot, right? So both of my variables, mean household income and mean age of kids, they have low p-values. So therefore, both of these variables are significant. So I'm going to keep them in the model. But here's what I'm going to do, ladies and gentlemen, okay? And this is where the true power of regression analysis comes in. I think that my revenue, okay, here's how I'm going to predict the revenue. Right now, my revenue looks like that. Let's go back. Okay, my slope or intercept is 667.8, 11.42 times. Okay, hold on. Where is this thing? Okay, right there. 667.8 plus 11.4. Okay, that's not times. 11.4 times income in the area plus what's the other one? 16.8. 16.8 times average age. Okay, this is what my regression looks like right now. Okay, but I'm thinking that I need also to add to the equation quadratic terms because they look like parabola, right? So it looks like I need to square the income because there is a shape that looks like parabola in my residuals, right? And I need to square the age. So in other words, I'm going to add, so this is beta 1 right here. This is my beta 2. So another one, beta 3 times income squared. Income squared. Plus, I need to add probably another beta 4 times age squared. In other words, now I'm looking at residuals. Residuals tell me what kind of curvature exists in the residual plot. And from that, I'm kind of using my judgment now. I'm trying to enter, additional variables or, combinations of variables, right, that I have right now in order to follow the same shape, in order to capture the shape of the residuals, okay? So essentially, here's what I'm going to do. I'm going to create a transformed variable, okay? Income squared. Income squared, I'm going to call, this was my x1, this was my x2. I'm going to call that x3, okay? x3. And age squared, I'm going to call x4. If I do that, then after that, essentially, my regression is going to look like this, times x3 plus age squared, that is x4. It is still going to look like a linear regression, right? But my variables, they kind of result from squaring of other variables, right? So I'm still going to use the same analysis as I did before. I'm going to say, I'm going to add more variables, but still we'll use the same linear structure, beta 1 x1, beta 2 x2, beta 3 x3, beta 4 x4, okay? So analysis still going to be the same. All right, let's try that. So I'm going to actually keep that and create a couple of more columns, right? So over here, next column number 4, I'm going to call it income squared. Income squared. And of course, the column will be computed using the formula, right? So I'm going to open up formula editor, click on the edit formula. And I'm going to say, well, that's income squared. So therefore, mean household income times mean household income. Okay? So that's going to be my new variable that I introduce into my model. All right? Didn't exist before, I made it up. And I'm going to do the same with age. So new column, I'm going to call it age squared. And there is a formula. Let's edit the formula. And that would be mean age times mean age. Simple as that. And there it is. So I just created two new variables, right, out of my existing variables. But I'm going to treat them as if they are independent. So as if I have x1, x2, x3, and x4. And still the same revenue, right? Let's see if I can build a better model from that. So same thing, right? I'm going to use the same platform, fit model. Predicting revenue based on now all these four variables. Age and income, and then squared age and squared income. And if I'm going to run the model, what do I see? Well, first of all, let's take a look at my R squared. Did that improve? Oh boy, it did, right? What did I have before? Let's go back to my previous analysis. Before that, I had R squared adjusted. Where was that? Here, right? Yeah, adjusted R squared was 0.2638. And I had these quadratic shapes, right, in my regression, in my residual plot. I'm sorry. Okay, this one and this one. Now that I added the quadratic terms to the equation, my R squared adjusted jumped from 26% to 86%. That's quite an improvement, right, in the model fit. Okay? And the variables, if you look at the p-values, all p-values are low, right? P-values for my initial variables, mean income and average age, they're low. Income squared is significant, age squared is also significant. So I built a better, much better model, right? And if you look at the residual plots, okay, residual plots kind of improved, right? Because here is your major residual plot, where you plot residuals versus the predicted value. Well, it still has some weird pattern, right? So for example, specifically, I can see that when the revenue is small, right? This is probably an outlier, this point right there, right? Because it looks so far away from the rest of the group, okay? But if I forget about that point, what do I see? Conical shape, right? Sort of. Because here I have small variability and then it gets larger and then it gets higher and higher and higher, right? So that's some weird pattern that we don't know yet how to address, but at least I got rid of this quadratic shape, right? There are no more parabolas, so if I'm looking, for example, at residual plots by each individual independent variable, this one doesn't look like a quadratic thing, right? What else do we have? This one looks fairly concentrated. So I got rid of the quadratic shapes. Okay. Now the question is, how do I get rid of what I have right now in the model is essentially heteroskedasticity, right, going on. And that I can try to perform other transformations. Typically, you can try and get rid of this kind of effect if you apply logarithmic transformation to your variables. So specifically, instead of predicting y, so let me go back to the drawing board, right? Instead of predicting y, my revenue, I can go ahead and say, well, let's transform y, okay? So instead of y, let's use log of y, logarithmic transformation, okay? And that's going to be my new value of dependent variable. Now let's see if I can fit now a regression into this as my new dependent variable, and these income, age, income squared, and age squared as my independent variables. In other words, I can try to do some funky transformations to make sure that now my residual plot looks more or less great. Uniform thickness, no patterns. But just by squaring the independent variables, I was able to drastically improve the quality of my model, right? So therefore, ladies and gentlemen, what we learned, the multiple linear regression is just the basic stuff, right? So after that, this is where essentially science meets the art, okay? What kind of transformation do we apply to what variables? Oh my God, there are so many possibilities. For example, let me show you another possibility, okay? Let me go back to my initial data. So here, what I did is I squared my initial variables, right? So I created new independent variables. Instead, in addition to that, I can say, well, there may be also interaction, okay? What does that mean? Well, that means that maybe in some areas, high household income and low age of children creates an additional boosting effect for the revenue, as opposed to other areas when your income is low and your age is also low average age, then it's completely different combo, okay? So there is an interaction between these two things, right? Age and the income. So therefore, how about that? I'm going to add yet another term where I'm going to take income and multiply it by the age of children. So I'm going to create a cross product interaction between the two different independent variables. And I'm going to call that a new independent variable x5. So expand my regression even more. Let's see if that helps actually. How about that? So over here I'm going to create a new column. I'm going to call it interaction between the variables, okay? And let's go make a formula. So I'm multiplying household income by the average age of kids in the neighborhood, okay? And that creates even entirely different variable for me, a new variable. And let me run now my regression with, how many independent variables do I have? 1, 2, 3, 4, 5, right? Well, they're not really independent, to be honest with you, okay? Because one of them is another squared, right? So therefore, I will have an issue with multicollinearity potentially, right? Because inherently, these probably are going to be correlated, right? In fact, let's take a look. First, let's build a model and see if we can beat our performance with this new improved model. Oops, what did I do? Here, right? I need to create a model, revenue, and the rest of them, they go into the model effects. Okay, and when I run it, what do I see in terms of my R squared? Oh God, that is a weird response right there, right? Where's my standard stuff, goodness of fit and stuff like that? Regression, summary of fit, right there, okay? Summary of fit, all right. So my R squared actually went up a little bit, correct? It was 0.8 something something, I can't remember it, now it's 0.9. So I was able to improve the model even more, right? So that basically, oh yeah, and another way how we can do that actually is like that. I don't have to create actually the variables in JUMP, don't have to create new columns. Instead of that, here's what I can do. I can go back into my fit the model window and say it's going to be revenue, and also it's going to be mean household income. Whoops, have to select them here. Mean household income and mean children's age. Okay, and I'm going to click on the button cross. Let's see what happens. If I click on the button cross, it adds the cross product, right? Mean income times mean age, and then I can just go ahead and put these variables as is. And if I want the second, now that part I'm not sure how I add the squared, so degree 2. How do I add the squared variable? That part I didn't quite figure out with JUMP yet. It's probably easy to do, but my point is I don't have to create a new variable by calculating that as a new column. I can actually use my existing columns and add more effects into the, it's probably actually cross with itself, now that I'm thinking about it. Cross with itself, right? So what will happen if I add mean household income and just click on the cross? No, nothing, right? It doesn't understand that. Yeah. That would be neat, right? If you could cross the variable with itself, that would be variable squared, right? But apparently JUMP doesn't do that. Okay? So, therefore, there is more to the regression that meets the eye, right? The simple thing that you can do is run the linear regression. Just basically take the variables as they are stated in your data set, but then you have to do some digging and analyzing, right? Look at the regression, at the residuals plot, see if you can spot any patterns, curves, and then after that decide what you want to do with them, right? So, and after that, basically it's the sea of creativity, right? You can square the variables, you can take the square root from the variable, all kinds of transformations are possible, right? So therefore, the more creative you get with regression analysis, the better models you can end up with, okay? That follow your data really closely and give you very nice fit, okay? All right, so my computer tells me that we're out of time pretty much for today because it's about to run out of electricity. All right, so let's finish it right here, okay? And you have a homework. There is one problem, and tomorrow we'll start with the homework, and then we'll do the exam, right? And then after that, there's going to be one more topic still remaining in this course, and that is called non-parametric techniques.